Welcome to Agentic Data. I'm your host, Joseph Moon, the CEO of Oxygen Intelligence. Today, we'll be talking about traces. This concept has been popping up all over my feed, and I think in tandem with context and context graphs, traces have been capturing the attention of many applied AI engineers. And today, I wanted to think about traces and what traces means for the development of robust agentic systems. I read an essay by Harrison Chase, the CEO of LangChain, recently, and I think it really encapsulates at least a first degree approximation of why traces are important and how we should think about them. So let's take a look here. This article reads, in software, the code documents the app. In AI, the traces do. TLDR, in traditional software, you read the code to understand what the app does. The decision logic lives in your code base. In AI agents, the code is just scaffolding. The actual decision-making happens in the model at runtime. Because of this, the source of truth for what your app does shifts from code to traces. Traces document what your agent actually did and why. This changes how we debug, test, optimize, monitor, collaborate, and understand product usage. If you're building agents without good observability, you're missing the source of truth for what your system actually does. That was a TLDR. Let's get into the rest of the essay. In traditional software, when something goes wrong, you read the code. When you want to understand how a feature works, you read the code. When you want to improve performance, you profile the code. The code is the source of truth. In AI agents, this doesn't work anymore. Why code doesn't document agent behavior? In traditional software, if you want to understand what happens when a user submits a form, you open handle submit and read the function. The decision logic is right there. Validate inputs, check authentication, call the API, handle errors. It's deterministic. Same input, same code path, same output. In AI agents, code is just scaffolding. Here's a simplified version of what agent code actually looks like. Agent equals agent, model equals GPT-4, tools equals search tool, analysis tool, visualization tool, system prompt, you are a helpful data analyst, ... Result, agent.run, user query. You've defined the pieces, which model, which tools, with what instructions, but the decision logic isn't in your code. It just orchestrates LLM calls. The actual decisions, which tool to call when, how to reason through the problem, when to stop, what to prioritize, all of that happens in the model at runtime. As the LLM drives more and more of your app, as it happens with agents, you have less and less visibility into what the app will actually do just by looking at the code. You can still debug your orchestration code, whether tool calling works, whether parsing works, but you can't debug the intelligence, whether the agent makes good decisions, whether it reasons effectively. That logic lives in the model, not in your code base. Traces as a new documentation. So where does actual behavior live? In the traces. A trace is a sequence of steps an agent takes. It documents the logic of your app, the reasoning at each step, which tools were called and why, the outcomes and timing. This means that operations you would do on code in the software world, you now do traces in the agent world. Debugging, testing, profiling, monitoring, all of these shift from operating on code to operating on traces. In traditional software, if two runs produce different outputs, you assume different inputs or different code. In AI agents, the same input with the same code can produce different outputs, different tool calls, different reasoning chains, different outcomes. The only way to understand what happens is to look at the trace. Why did task A succeed but task B fail? Compare the traces. Did your prompt change improve reasoning? Compare traces before and after. Why does the agent keep making the same mistakes? Look at the patterns across traces. How this changes building agents. When the source of truth for logic moves from code to traces, everything else follows. All the operations you used to do on code, debugging, testing, optimizing, monitoring, now need to center around traces. Let's look at what this means in practice. Debugging becomes trace analysis. When a user reports the agent failed, you don't open the code and look for a bug. You open the trace and look for where the reasoning went wrong. Did the agent misunderstand the task, call the wrong tool, get stuck in a loop? The bug isn't a logic error in your code. It's a reasoning error in what the agent actually did. Example, an agent keeps retrying the same failed API call 5 times before giving up. Your code has retry logic. That works fine. The bug is that the agent isn't learning from the error message. You only see this in the trace. Same tool call, same parameters, same failure, repeated. You can't set a breakpoint in reasoning. In traditional software, when you find a bug, you set a breakpoint in the code. In agents, you can't set a breakpoint in reasoning. The decision happens inside the model. But you could set a breakpoint in logic using traces and playgrounds. Open a trace at a particular point in time, right before the agent made the bad decision. Load that exact state into a playground. The playground is a debugger, but for reasoning instead of code. You could see what context did the agent have, what was in its memory, what tools were available, what did the prompt look like. Then you iterate, adjust the prompt, change the context, try different approaches, and see if the agent makes a better decision. Testing becomes eval driven. Now that the source of truth for logic is in traces, you need to test those traces. This means two things. First, you need a pipeline to add traces to your test data set. As your agent runs, you capture traces and add them to a data set that you could eval against. Second, you need to eval traces in production. In traditional software, you test before deployment and ship. In AI, agents are non-deterministic, so you need to continuously eval in production to catch quality degradation and drift. Performance optimization changes. In traditional software, you profile the code to find hot loops and optimize algorithms. In AI agents, you profile traces to find decision patterns, unnecessary tool calls, redundant reasoning, inefficient paths. The bottleneck is in the agent's decisions, and those only exist in traces. Monitoring shifts from uptime to quality. An agent can be up with 0 errors and still perform terribly, succeeding at the wrong tasks, succeeding inefficiently at 10x the cost, or giving correct but unhelpful answers. You need to monitor quality of decisions, not just system health, task success rate, reasoning quality, tool usage efficiency. You can't monitor quality without sampling and analyzing traces. Collaboration moves to observability platforms. In traditional software, collaboration happens in GitHub. You review code, leave comments on PRs, discuss implementation and issues. The code is the artifact everybody works with. In AI agents, the logic isn't in the code, it's in the traces. So collaboration has to happen where the traces are too. Sure, you use GitHub for the orchestration code, but when you're debugging why the agent made a bad decision, you need to share a trace, add comments on specific decision points, discuss why it chose this path. Your observability platform becomes a collaboration tool, not just a monitoring tool. Product analytics merges with debugging. In traditional software, product analytics is separate from debugging. Mixpanel tells you what users clicked. Your error logs tell you what broke. They're different tools for different questions. In AI agents, these merge. You can't understand user behavior without understanding agent behavior. When you see 30% of users are frustrated in your analytics, you need to open traces to see what the agent did wrong. When you see users asking for data analysis feature, you need to look at traces to see which tools the agent is already choosing and what's working. The user experiences the agent's decisions, and those decisions are documented in traces. So product analytics has to be built on traces. Make the shift. In traditional software, the code is your documentation. In AI agents, the trace is your documentation. The shift is simple. When the decision logic moves from your code base to the model, your source of truth moves from code to traces. Everything you used to do with code, debugging, testing, optimizing, monitoring, collaborating, you now do with traces. To make this work, you need good observability. Structured tracing that you could search, filter, and compare. The ability to see the full reasoning chain, which tools were called, how long things took, what it cost. The ability to run evals on historical data to monitor quality over time. If you're building agents and you don't have this, you're working blind. The logic that matters only exists in those traces. Pretty good essay. I think pretty succinct and pretty comprehensive, and really focuses on one simple fact that things were deterministic before because code equaled the steps that the computer took to execute something. And now the code is scaffolding and the operational truth is more probabilistic and is only available post facto. This is really a trade-off between precision and recall. So it's like relying on a human. A human has very, very high recall with lower precision than a computer system. That was previously the case. So a human knows how to do many, many different things, hundreds of different things, thousands of tasks, but perhaps is quite bad at certain things. And also they are not as reliable as a computer in repeating the same thing over and over again. Maybe you have some randomness and you have some errors, even if you repeat the same things over and over again. Now, computers and software, previous to agents, really acted like expert systems where you deterministically coded what it should do, what the computer should do, and the computer really reliably performed those actions. And if there were no errors of syntax, errors of hardware, and those more contained errors, then the computer really did what you asked it to do, and that was it. But the problem was you had to build so much deterministic software to perform action X and Y and Z and so forth. But now in the brave new world of agents, you could set up one agent, hook it up with thousands of different tools and let the agent really dictate how it should chain everything together to get to the end output, which means that you can write way less software, way less deterministic software, which means that companies and organizations and individuals could really run very leanly without having to pre-specify things. And so it's as if before, to do anything, you first had to write a bunch of books, and then those books got published, and then other humans read those books and then carried out those tasks. And then if you had to, change the behavior of other humans, you had to rewrite those books, publish them again, and then people follow those books, instructions on those books. Okay, but now you skip the book step, and what you do is you just tell the humans directly, hey, I want you to do X, Y, and Z, and then based on the humans' best reasoning practices, then the humans go and carry things out, something like that. And of course, because the context matters, communication is lossy, the humans are not going to exactly do what you wanted to do. So you have to iterate over that state space, and you have to really construct that chain of command correctly to get the right output, right? So you're relying for a vastly simpler architecture to trade off the recall versus precision dynamic, wherein you're dramatically increasing recall and slightly lowering precision. But the idea is that over time, precision will increase over time, and then you will have a very high recall and very high precision system at the end of the day. Let's think about things from first principles. If you have a deterministic workflow, you basically have a series of, you could represent the deterministic workflow as a type of graph object. This graph object can have some if-else statements and conditional statements that could propagate the chain of command. But generally speaking, you could think of it as a pretty linear progression of events and tasks as a deterministic workflow. Now, and each of these nodes are hard-coded, in a sense, specified via code. Agent native or agent embedded workflows in which one may have an agentic step as one of the nodes, meaning maybe you're calling an LLM in one of these chains, and that LLM is doing something with the data or the task at hand. So you could imagine, say, an agentic ETL pipeline that uses Claude, let's say, and Claude reads a document and then converts that into structured data, and then it moves that into a data warehouse. That could be construed as an agent native workflow. And then the most extreme version of all these classifications is the agentic workflow. The agentic workflow is one in which even the entire decision chain of how things propagate is dictated by an agent. I guess all of these should be dots. So these dots means that these are probabilistic. This means that this entire system it acts less like Newtonian mechanics. It acts more like quantum mechanics, where just by observing the states of the system, just by looking at the system, you can't quite tell what's going to actually happen at runtime. Because at runtime, what happens is it's as if the wave function of the possible paths that the agent could take collapses into reality. But it's really hard to know a priori which things are going to collapse. So in my mind, I think the transition from deterministic workflows to agentic workflows is a transition from Newtonian mechanics, Newtonian physics, and calculus-based models of thinking to quantum mechanics and really probability theory-based ways of thinking, wherein you think of everything as wave functions, probabilistic wave functions, and you think of when you, at the point of observation, the wave functions collapse and you get to observe that reality. So I think that's how things are propagating in terms of agentic workflows. And now what Harrison is saying in his essay is that the only way to know what has happened in your system is that you observe the wave function collapse, and then you kind of try to reason about why it happened, what happened, and so forth. And the set of data that shows you this wave function collapse is called a trace. And you reason through the trace in an observability platform, and then you collaborate over that to have a sense of what happened, how can I fix the system. So observability platform, bunch of people look at this thing, and this observability platform could become the canonical collaboration hub. So maybe what's happening is we're moving from a code-centric world where code is the canonical source of truth. So something like GitHub really dictated deterministic systems and how that operated. And moving towards a world in which traces, so observability systems, dictate and have the power over how agents operate. So both human agents and also AI agents operate in the wild. So I think this is a very profound shift that's going to happen that will shift the power dynamics from code-based systems to trace-based systems. And one should prepare for these platform shifts where the power shifts from one type of system of record, a code-based system of record, to a trace-based system of record. And effectively what is happening is we're finally in a stage where people do say data is very important. Data is all that matters in AI. Maybe data is going to be worth so much more than the code itself. And in an organization, last time we said an organization is a collection of data, tools, and agents. So agents are defined by code and the foundation models. Tools are just software, just deterministic software, mainly, reductively. Sometimes they're headless, so they're only designed for agents to use. And then you have data, which includes observability, as well as traces, as well as other types of context data, metadata, etc. And I think the part that is really critical to think about, where the power is going to consolidate, is really over this data platform. There could be many different renditions of this data platform, but it's very clear that at the very least, this data platform needs to have traces as a first-class citizen, and it must use these traces somehow. It's not for product analytics. It's looking at the analytics data and then also doing stuff with it to, say, refine the agents, refine the foundation models, refine the whole system, and also push those changes in some fashion. It might be through reinforcement learning and fine-tuning on the foundation model itself. It might be tweaking the orchestration layer of the agents, of the agentic system. It might be building in more headless tools, or it might be tweaking the data or adding more data. But that entire system, it needs to be very observability centric, and observability needs to lead somewhere. Observability needs to have a loop. So it has a flywheel, actually. So VCs and think boys and the intelligentsia, we love flywheels. So what happens is better observability data gets better inputs to agentic system, and then the agentic system provides more observability data during runtime, and then you also adjust the inputs to the agentic system, and this flywheel perpetuates. And this is where the lock-in of value is going to happen, and this is where the mode is in most enterprise systems. So there you go. These were our thoughts about traces and why traces are very important and why we're moving towards an observability first paradigm, a trace first paradigm, and the observability platform being the canonical collaboration hub for building better agentic systems. See you next time on Agentic Data.